Welcome back to the channel. In our previous video, we developed this leapfrog algorithm using slice notation in NumPy to advance the wave equation. So today we're going to implement this in Python code. So the first thing we need to do is import our modules. I'm going to import in Spider here, import NumPy as NP. What this means is that all I need to type is NP anytime I want to refer to NumPy, which is the numerical Python module. This gives us the power to use arrays. Next, we're going to import matplotlib.pyplot, a plotting library that's very similar to MATLAB as PLT, short for plot. Notice that Spider's giving me some warnings here. This is because I'm importing modules, but I haven't yet used them, so that's why I'm getting the warning, if you're curious about that. Next, I want to define physical constants. I'll put a note. For the code reader, define physical constants. Let's make the length of our system equal to 1.0 meters, say. Let's define a grid spacing. I'll let dx equal 0.1 tenth of a meter. I will define my wave speed. That's the tension, square root of tension divided by mass density we have seen, to be 1.0 as well. And I will let my dt, the time step, equal dx divided by c. So the distance that information can travel divided by the speed that it can travel that distance. There's a good reason for this. Let's put in a 1.0 times that quantity here. This restriction that the time step can't be smaller than this means that information can't travel from one grid point to the next in the code any faster than it can in the physical world, which is transported by the wave speed, which is the fastest way we can transport information in the system. We'll see that if we violate this, which is called the CFL condition, the Courant Friedrichs-Lewy condition, the code will become unstable. We'll break that on purpose just to see what the effects look like after we've got the code running. Next, I'd like to use an array to store information about space, so I'll use np.array, and notice that now my warning has gone away on line 1 because I'm calling the NumPy module, and this gives me the syntax. I see array object. I will use, actually not array, a range. This is a particular type of array that goes from start to stop in steps of size step, and we will go from 0 to L times, let's say 1 plus dx, comma dx. So we're going from 0 to, this will be 1 to, looks like 1.1 in steps of 0.1, but let's check what happens here. So if you take a look at a hand, you have 5 fingers. So interval-wise, we have 1, 2, 3, 4 intervals. So if I'm dividing up the interval from 0 to 1 into 4 parts, I need 1, 2, 3, 4, 5 grid points. So that's what's happening here. I'm going to have, if I have a grid spacing of 1/10, I'm actually going to have 11 grid points to include both ends. So let's run the code just to see what happens so far. And if I type x here, it will echo the value of x, and we can see it's an array. Goes from 0, steps of 0.1, up to 1.0, which is exactly what we want. So that is the desired effect. I might want to be able to refer to that 11 grid points, so I will say that the number of points npts is going to be len of x, and if I run that again and check out what npts is, it'll be 11. Good. So next, we would like to know how many time steps we're going to take. I'll say n steps equals, let's take 200 steps, and now we want to define the height of the string. So let's say that y equals np numpy dot sign of 2 times np.pi, pi is a number that's included in the NumPy module, times x, our array that refers to spatial distance from the left edge, and 2 pi x divided by the length of the system. So this will give us 2 half wavelengths, or 1 whole wavelength, over the length L of the system. Next, we'd like to define y to hold our spatial information, and remember that y is going to be an array. I'll fill it with zeros to start. This is the syntax for making an array full of zeros, and its size is going to be a tuple, and it will be n points long and 3 wide. So we have past, present, and future, as we talked about in the development of this algorithm. Looking at the algorithm here on the left, we refer to 0, 1, and 2 in the algorithm. So this gives us the space to hold that in an array of size 11, 3. And now let's define the dimension of the array. I'm going to use colon here to go from all the way from left to right and in the 0th time step, and that will equal np.sine of 2 times np.pi, pi is contained in the numpy module, times x divided by the length of our system. So this will give us over a length L 2 half wavelengths, or 1 whole wavelength of a sine function. So this will equal to 0 at both ends, convenient for our boundary conditions. Now we want to write our main program loop through time. So I will say for k in range 0 to n steps, the number of time steps we've defined, I need a colon to enter that time loop. And notice, because of my colon, my IDE nodes to indent so that I'm in the loop, because indentation is how we define being inside the loop in Python. We're going to say y of 1 colon minus 1. Remember, that just leaves out the boundary cells in our array, comma 1 equals, comma 2, our future, will equal reading our algorithm on the right there. I'll enter it in. So there we have our main algorithmic step implemented, and we want to tab ourselves back out to the main indent of the loop, and we will push our data back. So we've implemented the first 3 steps of our algorithm, just to see that things are working all right so far before we go any further. Let's let our number of time steps equal 2 and run the code once. And now I'd like to plt.plot x comma y, and I will use blue connected by dash circles. That's a lowercase o. And let's take a look at what our, let me clear that and refresh. So I see my first and second time steps there, and I'm clearly getting the shape of the sine wave. Why am I getting 2 of them? Because I have 2 rows entered in my, so if I wanted to see just the first time step, I could say here, plt.clf for clear the figure, and then hitting up twice, go back through my command history. I'll say y of colon comma 1, let's say colon comma 0 to get our initial condition, and look at that plot. So there is our very coarse grid, 11 data points representation of sine. So that's working as expected. Very good. So now I'd like to make sure that my time stepping is working correctly. I notice that I'm moving from 0 to 2 in my time dimension, but I haven't yet written into the 1 layer of time. So we want to make sure that that's working properly. Even though we have our time stepping here, we want to take care of the first step, which has to be different because we can't step over from 0 to 2 if 1 hasn't been written yet. So let's see how we do that. For our very first time step, we're going to say y of 1 colon minus 1, comma 1, y of 1 colon minus 1 of 0, plus we're going to take half of what we normally do to advance our time. So that'll be the value here. But we're going to do that at not time equals 1, but time equals 0, the only time we've defined so far. 0, 0, 0. Looks good to me. And now let's raise our time step to see that this advances properly in time, and we will run it. And now that we put that initial time step in, let's make sure we can visualize what's happening. So I will say plt.plot x comma y of colon comma 2, my most up-to-date time step, and I will make a blue connected series of dots, and I will make sure that I have a plt.new figure. We'll call this figure 1, and we will say plt.clf, clear the figure, so we have a fresh palette each time. And to make sure our axes stay the same while this wave moves, I will say plt.ylim will be negative 1.2, give us a little space to 1.2, and that should give us what we're looking for. Let's take a look, running the code. Seeing no motion, we want to make sure that we make sure to tell this to plot each time. So I will say plt.show and plt. Let's say pause for 100th of a second, 0.01, and running this again. Check it out. That looks like a oscillating standing wave on a string. Looks pretty good to me. So we're making progress. As a next step, I'd like to have the time plotted on the screen here. So I will say plt.title and let my title be, let's see, I will say as a string t equals percent 0.2f. So this will be a float with 2 decimal places, and what we put in that placeholder is going to be k times dt, and let's take a look at what that looks like. So we have our time in the vertical axis here. I see my oscillation. Looks pretty smooth, but we have only 11 data points, so let's check out what'll happen if I make my number of data points smaller. Let's say instead of 0.1, we'll do 0.05, twice as many data points, and oh, that looks smoother. Very nice. So we have this working smoothly in this simple initial condition. Let's try something a little bit more complicated. Let's try a superposition of states. Let's suppose I have y of everything comma 0 equals, let's say 0.5 times this case that we had before, plus 0.5 times np dot sine of 3 times np dot pi of x times x over L. So we have a mixed mode. We have a 2 half wavelengths plus 3 half wavelengths. Let's take a look at what that looks like. Running that, I see pretty smooth, looking good. So this looks fairly physical to me. Another thing we'd like to check is the wave speed in this code. So let's try one more initial condition. Let's suppose that we take a Gaussian wave pulse. So we will take y of colon comma 0 equals, let's say np.exp negative x minus L over 2. So we'll put our pulse in the middle and we'll square that. And we'll divide by some width squared. So we'll say width star star 2, and let's define that width. My width will equal 0.1. So that is the initial condition we're using to make that clear. Even though it's last, so it would execute its own anyway. We will take a look at what that looks like. So we have a pulse oscillating middle to edge and back. Looks pretty reasonable, but to make that a little bit more smooth, let's make this 0.01 more data points. We can see that that pulse splits, it hits the edges and flips as expected, comes back down, reflects, and comes back. And it does that just at t equals 2, so it took 1 simulation time to reach the reflected point and 1 additional time to reach the reflected point, so vertical again, and it's come back up to 1. So this is looking pretty reasonable that we have the expected wave speed and the expected behavior. We will check some additional conditions in the next video and also see how to turn this into a 2-dimensional code. So stay tuned, and I will see you in the next video.